Okay, this is the walkthrough of the new chapter, which is chapter 9, which is the waves chapter, or perhaps a better word is oscillations, which is all about movement of particles. We'll look at sound waves to start with, just because it's easy for getting everyone's ideas around things, and water waves because you can see them, but the ideas are about the same. So GCSE, effectively you learnt about waves of energy, particles passing on energy, air vibrating, water vibrating, light vibrating, and that is as it travels through from wherever your source is over here outwards to something that picks it up and detects it. It travels at certain speeds, and that transfer of energy is called a wave. So it's a mathematical way of looking at all of the ideas. And it keeps linking back to where we're going to get to with the maths, a simple equation. You may not look it, but it's one that you will see over and over again. Okay, the sine of an angle multiplied by the amplitude will give you that displacement. So let's build up to that, because there's a lot in it and there's a lot of other things as well. So the first bit is a review of everything you had at GCSE, the terminology of what's happening to these vibrations. They're going up and down. When they stop in the middle. If we look at the spacing for a longitudinal wave, again the spacing changes, goes in and out, but where they eventually end up is all evenly spaced out. That kind of is this rough spacing at the moment. Okay, so these are much tighter together, these are much more stretched apart. But if they all relax, they'll all be around about that kind of distance apart. So let's dive into the whole thing on waves, and it's a big chapter, a lot of ideas that you've done bits on already, but we need to get deeper into it. Okay, so these today are the properties of all bits of light, and then we can take it from there. Sorry, waves, which will lead us to the light, and then we can go on to further places from that. So what we're going to start with is basic properties. Okay, so we know roughly the terminology. We've got this idea of an equilibrium position where things stop when rulers vibrate, because you twang them. Fairly obviously they stop in the middle. When water finishes vibrating, it stops in that middle level. So everything is in that middle level. So what we're going to do is kind of use all that to make sure we've got our basic ideas. So firstly, wave speed is the velocity at which the energy transfers along. Okay, so to be clear, not how quickly this goes up and down, but actually how fast it travels along that way. So the crux idea of it all is that waves are travelling at a certain speed, nominated by c. Now you might have just learned this as a speed of light, but generally we're talking about the speed of a wave. So this is the distance covered per second. Okay, that's the basic idea, and hence the units are there. But it doesn't, of course, matter in terms of what actually is going on. So this is the distance covered per second by the, and this is the key word that we're going to use, the propagating wave. When we get to light, you'll see, for example, that light regenerates itself, so it's growing new waves, so like propagating plants. So by the propagating wave, as it carries, and this is the important bit, energy. Okay, so effectively it's how fast the energy travels along. Amplitude, this basically determines how much energy we've got. So the more energy there is, the bigger the size of the wave. It is not a straight comparison. So it's not double the height or double the displacement will give you double the energy. There's a bit more to it. but determines the energy transferred. Okay, and the key idea is that it's measured as displacement from center line or from equilibrium line. Okay, so I'll squeeze that in there because it's mainly about this. However, the generic phrase for the height of a wave is its displacement. The maximum displacement will give you the amplitude. Okay? Right, third one, wavelength. Simple enough, tells us how long a wave is. It's the length of a wave. But so it's distance between adjacent, because it's very easy to just talk generally, and actually it could mean several things, several wavelengths, for example. So distance between adjacent waves for 2 points at the same, a new word coming in here, at the same phase. I'll get into phase, but it's basically saying whereabouts on the wave you are, e.g. peak to peak. Sorry, that's shorthand there, peak to peak. That's when most people will do it, or on the way down to on the way down again. As it crosses the axis, crosses the axis. So those points are at the same point, those points are at the same point, the peaks are at the same point. So they are all at the same phase to each other, those pairs of readings. So it has to be for the adjacent ones. The time period is if this is moving, so you couldn't get it from this wave because this is distance wave. But if it was a time wave, shall we say measured against time, then it, like the wavelength, it goes from peak to peak or trough to trough, which is of course a negative peak. So yeah, as a more general way of doing it, time to complete one full oscillation, okay, vibration or cycle if you prefer. Okay, so that's quite a nice general phrase. So of the particles within it, they go up, they go down, they go back up again, down again. It's where they set off from, all the way up to the top and back down and back to that same starting position. So the time to take complete oscillation, the time for the wave to travel past you, or perhaps, easiest for my mind, is the time it takes to generate one wave. Might be the easy way of thinking about. And then the last bit is fairly straightforward. It is the frequency of vibration. So number of, shorthand there, number of vibrations or oscillations or cycles completed. Sorry, I'm going to say generated because it keeps that idea nice and clear, I think. Each second. And that links with that because that's the time for one vibration. This is how many vibrations every time, every unit of time. So key equation, which we'll use a lot, frequency is 1 over, oops, get all that in, frequency is 1 over the time period. Apologies for that, I'll leave that there while you make notes. Freeze the video as need be. Right, this is a big chapter because we cover so much ground, so let me just quickly run through. I've crossed that out there because that really fits in with an idea that we're going to use more in this next chapter. So it's quite a simple idea, but it leads to the more important one, which is phase difference. Now the crucial thing, as I say, is kind of giving this idea of whereabouts we are along the wave. And really it comes from the mathematics. Now it does give us a weird thing in that to make this work properly we need to measure angle properly. So here's a very simple idea to think about and use at the moment. We will actually go into the mathematics much later in the course, so to use it fully properly. But basically, instead of measuring an angle in degrees, we can measure it in something called radians, and it's a more proper unit. It actually makes a lot more sense. And the reason is it's to link the idea of angle, which we'll mention in a second, with the position along a wave in time. So effectively, one full cycle is equivalent to going all the way around the cycle, and so we can use the idea of angles. Now, a full cycle, to go from the bottom here, for example, negative peak, all the way to a positive peak and back down to negative peak, that will be one full circle. If you imagine that, it'd be the cycle. So that's 360 degrees. For what we're going to do, we're going to compare it to circumference, so once around the circumference. So that gives us an angle in radians of 2 pi, because 2 pi r is the circumference. If we go round twice, then we go through 2 lots of 2 pi, which is 4 pi. So it's an idea to be able to get in a convenient unit which has a bit of meaning because it's to do with the distance that it travels around, the circumference or part of circumference. Okay, so get used to some of these. Try and think about the fractions as we go through. Half a cycle, halfway is a pi. Half of that, a quarter of a cycle, is a pi over 2. Most people will be happy with. 3 pi over 2 for 3/4 of the way round, because it's 3/4 of 2 pi. Okay, 1 1/4 times round, 2 1/2 pi, etc., or 5 over 2 pi. So you can work it all out in half pi's for every right angle if you prefer. Now, before we go any further with that, with the mathematics, we need to just kind of summarise all our ideas from that first bit. So what we've got for this next section is that we're actually, when we're talking about waves, we're actually going to talk about the particles that transfer the energy. Okay, the fact is the particles wave about. I don't know that's where the name comes from, but they oscillate back and forth, they vibrate up and down, they vibrate on the spot, they don't flow along. So they vibrate on the spot, and it's the vibration of the particles that is actually what a wave is all about. So it's particle passing on energy to particle, passing on energy to particle. So the interesting thing is we can get past this next bit if we think about it in that way. So all particles, okay, in a wave that make up a wave, and I'll say in all types of wave. Now at GCSE you only did 2, but all types of wave move with something called simple harmonic motion. It's simple, it's harmonic, cyclical, and it's about movement. So we are going to go into that next year. It's a proper full-on physics topic, but we're going to just work on the idea that it moves. If we think about these as they vibrate up and down, they go up, they slow down, they reach the top, then they accelerate more steeply back downwards. Okay, so here's our steep bit, and then they'll slow down again, and then they'll stop moving, and then they'll start moving back up again. So the particle itself is just moving back and forth. If it was one of these types of wave, which we all know is a transverse wave, no it's not, I did that in the lesson the other day, I'm going mad, longitudinal wave, okay, the vibrations is actually back and forth that way. Okay, so I'll put it over the edge here. That's your vibration as the wave travels along with a speed in that direction. So that's, I'm going to say, the direction of the wave. Just be very careful when you're writing that or saying that in a question. It's not the direction of the vibration. Okay, it's the direction of which the energy is travelling, direction of wave motion. Let's put it that way. Okay. So they're vibrating back and forth, not up and down. But the movement over time is they'll speed up, they'll slow down, they'll stop, they'll go backward again, speeding up, slowing down, stop, and then they'll go back again. And as the ripples spread along, they still move from their equilibrium position up to a maximum distance. The louder the sound, the more those will move back and forth, the bigger the oscillation. Now, the most obvious version of longitudinal wave is, of course, sound. Okay, I suppose we should also say that that's all types of sound. So we look at ultrasound quite a lot. We use it with the medical topic next year as well. Okay, so it's probably worth mentioning that. Anything to do with sound travels like that. But we also have seismic waves, earthquake waves. The ones that travel fastest, earthquake waves that travel fastest, are because they're pulsing together. So they tend to travel faster than other types of wave because all the energy is going into moving in the line of which it's moving. So seismic primary waves, or P waves. Okay. So if you're stood on the ground, for example, if I turn this around and the earthquake's coming up out of the ground towards you, you will find yourself moving up and down on the ground. So if you're stood in an earthquake, the first thing you'll notice is the ground is going up and down. Okay. And that's the primary pushing waves that come up. Later, you get, so I'm going to work down here, the second type of seismic waves. Okay, and they're second, or secondary as they're known, because they're slower, they travel more slowly from the same place, they just take longer to get there. And if you are stood, again using that idea, if the earthquake is under your feet and you're stood here, what you'll start to do is move from side to side and buildings start to sway and things like that. So it might not take long if you're too far from the earthquake epicenter, above the point where it's coming from, but you'll find that the actual movement is totally different. Now this one, vibrating from side to side, the classic wave that most people draw, when it is the distance, okay, then we can measure the length between different waves. So this is like a photograph at one instant in time, so it's worth putting at time t. Okay, so at that moment, take a photo, you got peaks in different places, you got dips in different places, negative peaks in different places. That is a transverse wave. And crucially, you've got the same vibration, but the vibration is, as I'm sure you learned at GCSE, perpendicular to the direction of travel. Okay? So if that's the direction the wave is moving in, the velocity it's moving in, that's your vibration here. Okay? Now, both of those, if we consider a particle, I should say, add one more, lots and lots and lots of different types of transverse waves. About the only one that isn't, about the only one that we use all the time, that is the other type of wave, is the sound one. P waves as well, but we don't tend to mention them much. I do have an activity I'm going to get you to do, but otherwise it tends to just be about sound. Every other type of wave that we consider is like this. There are others, it should be said. If you are at the beach, then what you'll find is, if I just put that in there and do a little sketch, is that because it's not about a rock, for example, splashing water, in which case we get our ripples spreading outwards, okay, nice and evenly. If we're at a beach, the wind blowing across the top is actually what is causing that thing to to go. So as the wind blows, what it does is it lifts up the waves, and so you get an asymmetric kind of cresting. And of course, when it gets nearer the beach, those tend to get blown over as it slows down. That's travelling too fast. The bottom travels slower as it reaches the beach, and so it curls over. Now, if you were to drop a ball on this, what you'd find is the ball would get pulled backwards towards the wave. I'm sure you've experienced this yourself. Let's do that in a different colour. So it gets pulled back towards the wave. It then gets lifted up as the wave comes past it, and then as it gets near the top, it's washed forwards. So actually what you end up with is a rotating motion. Okay, very similar to a Rayleigh wave is another type of seismic wave, earthquake wave. And the grounds coming after P and S, they'll actually start making the ground rotate and can turn liquefaction, making solid sandy alluvial soils behave as though they're water because they're not bonded together. So things sink in alluvial soil, farmland type soil. Buildings will sink if an earthquake hits rather than fall over because they're being wobbled. So lots of different types of waves. The particles can still be described in basically the same way. The maths is a little bit harder. But the crucial thing, and I'm going to put electromagnetic because that's one we do mostly. So we're going to look at light or radiation, as we will mention. They all look the same if the axis is for time. Okay, so we're going to use this idea of cycle or time period. Okay, period will do, but most people say time period just to make it really obvious. We still have the whole idea of positive direction, maximum positive direction, maximum negative direction, but it's all about oscillating, and it doesn't matter if it is oscillating up and down or forwards and backwards. They still have a maximum energy at one point and a minimum at another. So if we put those together, what we end up with is a nice idea where, as I described on the first cover, the actual size, the displacement in the y-axis, so I'm going to call it y, is a sine theta. Okay, sine theta maximum is 1. So if your wave is 20 meters high, it would have to be 20 meters times by sine. So we go anywhere between 20 and minus 20. Okay, so it's that maximum minimum value as such, or sorry, maximum and negative maximum value. Now, if we go much further down, then what we end up with is the idea that those go together. Excuse me a second, I've just got a little fault with something going weird over here. So, there we go. What we can say is that we can relate it to the idea of the rotation rate, which we call omega. Okay, now for us, omega, I'll put it now, is angular velocity. You do not need to know that this year. Okay, but the idea is angle per second rather than meters per second. Okay, so that's our unit, radians per second or rads per second. And then what we say is basically the idea is for one cycle, okay, one full cycle, excuse me, basically the angle is giving us that idea of how much we've gone round in a full time. So a full circumference, 2 pi r. The way we measure angle gets rid of the r, more of that another time. The time it takes, so full circle, full time, that gives us omega. And what we can do is we can just put that into the equation where y equals a sine omega t, so 2 pi over capital T multiplied by little t, and all of that gives us the idea of fractions. Okay, so how much of the little t, how much along in time compared to the full cycle of time there. Okay, so this is time ticking on, gives us a little t. Now that's a bit mucky. It's great as an idea because it's about this idea of fraction. Should we make that slightly different, and you might see that more easily. So 2 pi t over t. There we go. That might make it easier. So part of the time over the big time, full angle, we give us our part of angle. There's a bit of logic in there, but I'm not going to go dwell on it. We do happen to know, so we shall say, but 1 over t that we've got there, 2 pi t divided by t. So 1 over t is frequency. Yeah. So what I can do is come up with an equation that's a little bit more happy looking and a bit more user friendly. 2 pi times by f times by t. And f is of course frequency. So by measuring frequency, by knowing amplitude and knowing how long the wave has been rolling along for, we can work out how high the wave is at that point. Now, the mathematics of that fits in with other maths because, again, not all waves travel along as a nice straight line. They almost rarely do, unless it happens to be made of a rope, which you are flicking up and down. So what we really get is things that spread out. And I'll come back to this box at the bottom. But this spread out, like sound, radioactive sources, even gravity, although we'll talk about that in a different way, means that as the energy spreads outwards, it spreads out in 3 dimensions. What that means is that it spreads out more thinly. So it's rather like a balloon that you try and stretch. Now, my example is a butter gun, and I've explained it in class, but it's just the simple idea that if you try and fire a button of energy, okay, a button of butter, a blob of butter, if it was to be fired from a certain position, if we were to spend it outwards in all directions, you'd end up with firstly a mess, but also perfect ripples spreading outwards. So think of light and other waves rippling outwards rather than the rays going, and you'll find it a little bit easier to get your head around most of this. And if I just take a section of light, so there's a ray and there's another ray, for example, and sheet, I'm going to put a third ray because I know what this is going to look like. I'm going to take a size, and this effectively is perpendicular to these rays. Okay, so I've got effectively a small bit of this bubble that's spreading outwards, a little bit of that surface area. Okay, now I'm going to just put an A for area there at the moment, but I'm going to add to that in a bit. Now, if I take myself halfway back to the object that's giving out the rays, then if you make a mark, and you can do this very carefully, you'll always get it to work right. We'll make it the parallel shape, so as though our bubble is still swelling but it hasn't got that far. If you do the kind of playing with that, you'll find, again, let's get that parallel. What you'll find is that effectively you've got the area getting bigger and bigger and bigger. So if I was firing butter onto a slice of toast, well, if I put the toast twice as far away, so for example here I've got a simple distance r, I'm going to call it r because it's actually a circle, so that's radius, and if I have that at 2r, okay, what you'll find is that if you've done it just to make sure it's nice and careful in terms of distance, so it looks about right from there to there, then actually you'll end up something twice as wide and twice as high. Mine doesn't look quite right, I've got a bit of a wobbly line ray going out there, but basically that, if I take that area, then what I've got here is actually 4 times the area. So my butter is spread over a bigger area, but it's obviously thinner. Okay, so what we've got going on is that over here I might have a certain intensity, but here I've got a quarter of that intensity. Okay, so that kind of colouring in as such won't be anywhere near as dark and as definite as that. So, further away you are from a light, the thinner the butter, the thinner the energy that hits your eye, the less bright it looks. Now, if you put in the whole idea, what we've got here is we have some sort of power, and that power going into this source, into this light bulb, actually makes, of course, rays go off in all directions. Okay, so just to kind of give that hint that it's in 3 dimensions, we can keep these are big surface areas, etc. And this is kind of important. So, for example, if you are going further away from something, because there's not as much concentration of energy, if you want to capture the same amount of energy, you would need a bigger capturing surface. Classic example is solar panels. If you go out into space and you have something that's catching its energy from the sun and it's going further from the sun to the planet or moon where it's going, you need bigger solar panels so that it still carries enough energy, captures enough energy to actually light up the instruments, make the communication systems work, etc. Now, still slightly dodgy in terms of, say, distance, but if you were to repeat that and go up to there, then you'll get the same system again, and you'll find, if I just try and draw that carefully there, that's not quite the right angle again, but the idea is there. What you'll actually find is that when it hits that ray there and goes up to the one at the top, etc., etc., because that's 3 times radius, I'm sure you can guess by now, 3 times the distance from P, you're going to end up with 3 times wider, and that's definitely not to scale, 3 times higher, and so you end up with 9 times the area. Okay, so that means the intensity is 1/9 of the intensity that was here. And you can keep following the pattern, but we can put it together really nice and mathematically. We've put those 2 things together, it works really, really well. But how do we get that 9? Well, we get it from this idea of radius. 9, 3, 4, 2, 1, 1. It's obviously a squared pattern. Okay, so what we'll do, just go back 1 square to the bottom of the previous page. Intensity is defined as the radiated energy hitting a surface of 1 meter squared, or 1 unit unit area, every second, because that tells you the brightness. If it's throwing out twice as fast, it will still have the same, going to quarter, going to 9ths, going to 16ths, going to 25ths of the brightness as you go outwards. So, power, hence the unit is watts per meter squared. So if you want the intensity, you end up with the power of the original source divided by the whole surface it's spreading out over. So 4 pi r squared, the area of a sphere. Okay, in the data books you might have it slightly differently, but it's power over area, which looks a bit similar. I will put that with a health hazard because people will get confused and think power being pressure over area, which is not an equation. You'd be wrong. So, go back to this and use those 2 logic, and we put them together. Just put those together a second. If you want to work out the way through this, then the mathematics and using the logic, all the full version, is that basically the intensity at any distance from a position is proportional to 1 over r squared. Okay, this is known as the inverse square law. It does say in the notes above. And this is so common in lots and lots of physics. twice as far, only a quarter of the strength. Idea works with kinetic energy, lots and lots of other places. Now, if you wanted to work out how bright it was, you can either use logic, or what if it's 2.5 times the distance, etc. You need a bit more. So the other way of looking at this is to use in questions, in comparison, that is. So comparison questions, how much brighter is it, how much less bright, or how far do you have to be to get it a certain brightness. Let's just move those together. So I multiplied by r squared by taking the r across equals some constant. Okay. And that constant, will be exactly the same for the same light bulb. So I should say for the source. It might not be a light bulb, so whatever is giving out the light itself. Okay, so bit of an idea, the power is spread, do you get the joke, more thinly. Okay, so my butter is spread more thinly, which is a lower intensity. Okay. Spread more thinly over a larger area, which is why it's spread out more thinly. Okay. Please notice though, if you use the logic, how much butter is on there compared to there, the same. It's just spread out wider. Okay, so the total, crucially, the total power, okay, on the area is constant. Okay, so unless you start playing around with the brightness of the sun, for example, then you're always going to get the same brightness of light, same intensity of light, wherever you're measuring it. Okay, so that's a big idea, and it has to fit in with this. So in real life, these waves aren't constant, they get smaller, but that's because they're spreading outwards. Okay, so just have a think if you've got a question, or if they mention the word intensity, it's all about that spreading out of your butter. Now, if we think about that, then that kind of hints at the power, the wave itself carries the power. In other words, how much energy is carried itself. Now, in a way, if this was a light bulb, the easy way to think about it is just exactly the same format. If we had waves coming out of here, that's because we've excited the atoms, etc. If you want to do it clearly and smoothly and cleanly, you tend to use an AC wave. Well, we know the power of a light bulb is already given to you, so basically we know that you could say IV, but going through a resistance of a bulb, it's just the I and the resistance. The V is actually over the battery, so it's not a useful form. When we go on to electric circuits, you'll see that. So the best equation to use for power is basically I squared R, which you did at GCSE. Yeah? Now, I'm going to say, just to make the hint, because that is true all the way, so I'm going to think about the maximum power, which is fairly obviously, I'd say, from the maximum current, and even more obviously is at that point. So it's where you got your peak, or there, or there. Okay, so that's where you're going to get your maximum power. And if you think what that means, okay, it actually all links in together. So what we have is the power of a wave effectively, because the resistance is constant, I should say, because that's constant, it's basically saying that if you had a current wave, the power given out is the square of the current. Okay, so the square of the amplitude itself. Okay, so interesting idea. Power is equivalent to, that's a 3-bar equals, so equivalent to amplitude squared. Okay, that has come up occasionally. We'll look at it because when we do quantum electrodynamics and photons, we get the same kind of idea about how much energy it delivers, which makes sense because whether we're thinking about quantum explanations or wave explanations, they both still transmit and carry energy as it travels along. So you've got the idea there. It links in. If you wanted to link it with intensity, then effectively you could put the two together. Okay, so you could have the intensity gives us that idea of area. Power gives us that area. So intensity is going to be power over area equals basically amplitude, or is equivalent to amplitude over area. Amplitude squared. If you wanted to, you could of course say, well, the area is the width, or r, times square as well, because you can get your 4 pi r giving you, 4 pi r squared giving you area. So you could actually turn that into amplitude over r all squared. Okay, so just a little bit of playing around with it, but just link it back. The power is that size squared, whatever that scale is, amps or milliamps or kiloamps. Quite high that one, but it could be. And then that kind of gives us our brightness, but the brightness fades out. What's the brightness fade out and how does it fade out? That's where your mathematics comes in, and basically all of it links together and it all comes back to giving these numbers and making the link between the speed, the amplitude, the wavelength, the time period and the frequency. The only thing I haven't mentioned is what you did a lot of at GCSE. It's probably worth reminding you that, of course, C equals F times lambda. Okay, so your wavelength depends on the other two. I should say here, this is, it's not how we write it at GCSE, but velocity is distance over time. For those who have done it will know it's displacement over time, and we use letters that don't look like they do, so I'm going to leave that for a bit. But you don't find the speed of a wave from that, you find the wavelength, or you should find the wavelength from that. Okay, that's how you find the speed of something, distance over time.